Hello. In this lab we will see activity 2 of the magnetic induction. So once again the objective is to experimentally prove Faraday's law. Now what we will do is to rotate a coil under a constant magnetic field, and we'll see that that will produce an electromotive force. This is again the formula. Electromotive force is proportional to the number of turns on the coil and the change of the flux with time. This minus is Lenz's law. That's something we didn't explain, and we'll explain now. Lenz's law means that the electromotive force is opposed to the change of the flux, meaning that if the flux increases, then the electromotive force opposes to that increase. This is important to explain why we have peaks up and down depending on the number of lines entering in or out. So once again, this is the model. Okay, we have a permanent magnet, and in this region we have more field lines, in other words more flux, than in this region, for instance. Okay, and if we go far away, of course, here we have very little or no lines, and therefore the flux will be almost zero. Here maximum, here would be minimum. Okay, the flux, remember, is the dot product of the field, magnetic field, times the area. The area is the cross section. Okay, the cross section area, and the cosine of both, right? This is Faraday's law, and this is the thing we will check, that if there is a change now because of the change of the area, because we will be rotating and therefore the area will be different, right? Cosine will run from 0 to 360 degrees, therefore the area exposed to the flux will be changing, and therefore if we change A with time, then we change the flux with time, and therefore we have an electromotive force. Once again, this is the way we will check Faraday's law now. Okay, and this is a good model. Okay, we have a rotating coil, in this case one single coil, but we can have many turns, and this coil is rotating on a permanent magnetic field, for instance created by a permanent magnet, okay, constant magnetic field. And since the coil is rotating, the area exposed to the field lines is changing with time, and therefore the flux is changing with time, and that will produce an electromotive force. So let's do this activity first as a real taped example, and then we will do some simulation. So the materials we will need are basically a coil, some rotating mechanism, okay, to put this coil on a rotary platform like this. We of course need a permanent magnet to create the field lines, and we need to check using a voltage sensor again the current and therefore the voltage induced on the coil when rotating this coil under the permanent magnet. We can have either a digital multimeter or, more interesting, scope. Why? Because we will want to see the change with time. Every time we need to see a voltage, in this case, changing with time, it's much more interesting to use a scope, because we can see the waveform. Okay? So unfortunately this time I didn't have the chance to make this experiment for you. We will use another experiment we found on the internet, which explains very nicely this effect. Now in this experiment we have a coil and a magnet. Instead of rotating the coil, we will rotate the magnet, which is basically the same, right? One is rotating. And the LED here represents the EMF. In other words, if we have light, that means we will have a current going through we will have an electromotive force, and therefore we will have some light on the LED. If we have no light, that means we don't have any current, we don't have any EMF. Alright? So let's see how we can do the experiment. Again, we are now rotating the magnet, and as you can see, we can have light, not light, light, no light, light, no light. Alright? When we have no light, means we have zero voltage induced, zero electromotive force. When we have maximum light, we have maximum electromotive force. Okay? And we can do this with several other devices. That's the physics principle behind the electric motors. Okay? Electric motors, electric engines, that's the way they work. Having this changing of exposure area on a permanent magnet, for instance. Okay? As you can see, we can have, in this case, instead of having an LED, we are having a coil here with a lot of turns. And we are measuring there, in the multimeter, we are measuring the different values for the voltage. We are measuring voltage. Okay? Same with LEDs. Basically, again, light means we have some voltage induced, some current induced. No light means we don't have any current, any voltage induced. Okay? So let's do a simulation. Okay? This time we found this simulation for you, and as you will see, this simulation represents very well a rotational coil under a permanent magnetic field. Let's do the simulation. So this is the simulation running, and as you can see, we can increase the speed of rotation. Okay, these are radians per second, that's the speed of rotation. If we increase the rotation, of course, we will have more cycles both on the flux change and on the induced EMF. Okay, to see it more clearly, I will go for a very low speed, low rotation speed. Okay, so here the interesting thing is to see what is the relationship between the flux linkage top graph and the induced EMF, the induced electromotive force. Down. As you can see, I will stop it. Okay. For instance, as you can see, when we have maximum or minimum flux, we have zero induced EMF. If we have a change, either decreasing or increasing in the flux, we will have the corresponding increasing or decreasing on the induced EMF. Alright? And these are the things you have to explain. You want to explain why we have this effect. Okay? Why we have zero voltage induced, electromotive force induced, when we have either maximum or minimum flux, and why we have this increase when we have this decrease, and look, here we have a decrease when we are going even down here, right? In this semicircle. When we are increasing now, then we are decreasing, and when we are increasing here, we are decreasing. These are the shapes you want to explain. Why you have this effect compared to this, okay? And to do so, you have to think about Lenz's law. Lenz's law really explains this effect. Lenz's law is the minus in Faraday's law, okay? The change of the flux with time opposes to the electromotive force induced. Okay? So once again, here are the things you must do. You want to run different experiments in this physics lens simulator, playing with different rotation speeds. Do not forget to take screenshots. And you want to justify this shape of the induced EMF with respect to the flux linkage. In other words, why when we have maximum or minimum flux, we have zero electromotive force, and why, when we have zero, we have maximum or minimum decreasing or increasing depending on which stage we are within these cycles. Okay? Remember, you want to use Lenz's law, the minus, on this Faraday's law. Alright? Please do not forget to take screenshots for your lab report. Okay? And again, both activities, as you can see this time, they are very qualitative. They can be combined into one single Lab10 report. And that's all you have to do. Good luck.